continue where we left off. We're doing multivariate functions. And I believe we left off just before the limits. So what we're going to do is evaluate the given limit or statewide does not exist. That shit just looks like barf. That shit just looks like barf. I could never drink it.
This?
Yeah, I'm sure.
Oh, yeah.
It just looks like barf.
It took me like so long to get over it, but yeah.
What is it?
It's basically like, you know, like juice. It's basically like
It's green juice, green machine. It's
Yeah.
like a bunch of greens that they blend together and juice it. Looks nasty.
I thought it would taste like just like blended up like broccoli and like.
So I think they put apples and bananas in it.
Yeah, but it's pretty fruity. It's like very pretty citrusy. So. I used to only like the mango flavored one, the orange one.
Strawberry banana is the best.
Strawberry banana. Never go wrong with that one.
Well, why not just try straight substitution? See if that gets us. Two to the fourth times two to the fifth. What's two to the fifth? Times three. So 3 squared is 9 times 7, 63. And then 63 times 4.
256 minus 4.
252.
What is it?
52.
63 times
Oh, 64.
4. So it's 252.
Yeah.
And then 96 minus 252. What's 252 minus 100? Add 4. It would be 156.
Yeah.
Negative 156. There's your limits. Again, we have straight substitutions for that. What's cosine of pi over 4? There's your limit. Root 2 over 2 times pi. So again, try direct substitution. What do you get? What's that called? What is it?
Undetermined?
Not undetermined. It's indeterminate. This is indeterminate form. There's no algebra we can do. There are 2 methods that I'm going to use both of them. Let's look what happens if we approach the origin along an arbitrary line in the form y equals mx. Well, as xy approaches 0, 0. What do I want? No. I'm replacing y with mx. So now I can just treat this as a single variable limit. X is approaching 0. Notice as x approaches 0, y is also approaching 0, so this does work. Right, that line is going to approach the origin. Since x is approaching 0, we are about to cancel out the x squares. Right, so that means x will never be 0. That's just 1 over 1 plus m squared. What do you notice about that limit?
Natural law. It's all it's really natural law.
You don't need to.
We factor that out.
How about factor?
And plus 1 and then plus 1.
That gives you a 2 and a You're overlooking it. It's very obvious. Depend on n. It just depends on n. That limit depends on the slope of the line. So if m is 1 versus m is 2, aren't they different limits? This limit does not exist.
But he said it.
That limit depends on the slope of the line.
Okay.
So different lines gives you different limits, which means the limit does not exist.
Oh.
Right? The limit's not the same
Oh.
on all those paths.
Oh.
So the limit can't exist. Since it depends on n, the limit does not exist. Another way you can do this is you could just pick 2 lines. You could do like y equals 0 and x equals 0 and see what happens. Those limits also won't be the same, and they can conclude that it doesn't exist. Now we have to be careful. If that n wasn't there, that doesn't mean the limit exists. Right? All that showed was the limit's the same for all those lines, but not for every single possible path.
So you have to try that.
So that doesn't mean the limit exists. So they have to do something else.
Check with another one.
There's an infinite number of paths. So you're going to have to either find a path where the limit is different, or you have to do some kind of algebra. Here's the second way to do it. Convert it to polar. What does x equal in polar coordinates? And what about y?
X squared plus y squared is 1. Squared.
As x and y approach the origin, r approaches 0. Right? Because x squared plus y squared is r squared. Again, where r is approaching 0, so you can cancel out the r squareds. Equals cosine squared of theta. That limit depends on theta. And it means it depends on the angle at which we're approaching the origin. So once again, the limit does not exist. Because it depends on the path. And so you're done either one. Evaluate this, or state why it does not exist. Again, just try direct substitution when you get. You get here. Get the determinant again. Let's convert to polar and see what happens. It's going to be a limit now as r approaches 0. X is r cosine theta, y is r sine theta. Numerator is going to be r squared times cosine theta times sine theta. What about the denominator? And since we're approaching 0, you're allowed to cancel out those r's. And remember, Calc 1, there's a theorem that says those limits will be equal. Right? The particular result I'm using is if f of x and g of x agree at all points except at x equals a, then the limit as x approaches a of f of x equals the limit as x approaches a of g of x. Right? Those two functions agree everywhere except at all equals at r equals 0. What's that limit? What's the limit? Zero. Right? R is going to zero. So it doesn't matter what cosine and sine are doing. So I would limit zero.
So the always better to convert to polar instead of doing the y equals mx because
It depends on the situation. You can get some pretty hideous looking functions converted to polar. Like if you start to involve natural logs and exponentials, where the algebra doesn't become as simple. And then you have the same thing now if it's a three-variate function. Except keep in mind you also have two additional equation systems. You have cylindrical and spherical that you can convert to. And in general, three-variate limits are more of a pain than two-variate. And then four-variate even worse. Five-variate even worse. So these limits are not as simple as single-variate capital limits. In general, they are a lot worse. But keep in mind that the meaning is the same. Are there any questions on the multivariate stuff? What came after limits? Continuity is built into limits.
like in count one,
What was after limits and continuity?
concavity and all that stuff.
That relied on something.
Derivative tests.
Derivative is next. Okay, problem. Derivative is with respect to an independent variable.
Partial.
With multivariate, you have more than one. So you can't really take a derivative. We take what's called the partial derivatives, which as we'll see is very similar. And then there is what's known as a total differential for a function, which has a similar meaning to the differentials in Calc 1, both of which are important, as you two no doubt know, in differential equations. Again, why Calc 3 is not a prereq for DQ, I don't know. But here we are. So get into your group. Next will be 30 minutes for the worksheet, 10-minute break. That'll take us to what, 2 o'clock? And then we'll do partial derivatives. And again, we're at that stage, we're at 75 minutes, and then 25 minutes next class. So next class, we'll start with the worksheet, and then a second worksheet at the end, because then you have 100 minutes. You also need your quizzes coming up. I think it's the third quiz, right?
Okay.
Yeah.
Is that this week?
Yeah, it'll go up Wednesday after class.
Speaking of which, will they be graded?
So many people take them, so I'm not gonna start grading till I have them. About next week, I'm hoping I'll start. And once I start, they can take generally a day or two. Okay, continue.
What happened to that?
What, no, you just put it back up. Press on the button.
I actually like these desks. Oh, there's a button. Okay, I didn't see that.
So partial derivative. First, let's see who really remembers their calculus. What's the definition of derivative?
No. Limit h to 0.
I'm going to use delta x instead of h, but you
Delta
can use
x
whatever.
F of x minus f of del x minus delta h. No, go ahead.
No,
No, you got it. I don't remember. It's like f of x minus f of a all over something. Or am I?
That's out of point. F of x minus f of a all over x minus a as x approaches a.
Oh, is it x plus
it's
h?
minus over delta x.
Yeah.
That limit. Here are two partials. We're dealing with two variables. So two notations. Partial f partial x, or f sub x. Right? So that symbol, this symbol, we read it as partial, but that is actually a del, del. Not to be confused with the del operator that we'll study later. My favorite operator, by the way.
Does it delete?
No, it's a really cool operator. We'll study it, don't worry. In fact, without that operator, none of this would exist. It's one of my favorite operators. So notice the definition, right? So for x, limit as delta x approaches 0, f of x plus delta x comma y minus f of x y all over delta x. Right, and that's similar here. So notice what's happening. With respect to x, your y stays constant. Your y is not changing. And then with respect to y, notice your x doesn't change. Three variant, exact same, except now you have that third, right? Again, notice, with respect to x, it's only your x changing, right? The y and the z stay the same, right? Then the x and the z are staying the same, and the x and the y are staying the same. And we can, of course, extend this to any number of variables. Interesting tidbit too, right? This notation has a special meaning. You know what it is?
Take the
Right, so df dx had a name. That notation is called something. Do you know what it is?
correct. No. Same thing on
Leibniz notation.
Oh. And that was
Who discovered calculus?
Newton.
both at the same time. Or sorry, Leibniz first, right?
Leibniz wrote the paper first.
But you didn't submit it.
Oh, he submitted it. So why is Newton credited?
He's more famous.
Back in the day, the committee who votes on what newspaper to publish was chaired by Newton.
Oh.
So even though Leibniz's paper was submitted for publication first, because Newton was the chair, Newton's was published.
What?
So Leibniz is actually, but it was stolen.
Why is it the brain industry was just like all the great inventors you learned about when you were like a child? Later in life, they're like, yeah, that guy was actually just Edison.
Einstein's idea also was kind of stolen.
Because he used to work at a patent office.
And he kind of saw something, and it kind of sparked his idea for general relativity. But his is a little bit different because it wasn't about general relativity, but it was an idea that he was patenting that gave him the idea for general relativity. And so there's your little trivia knowledge for the day. Newton didn't actually discover calculus first. We're going to use the limit definitions to find the particles. Again, so just like with Calc 1, right? When you first learned the derivatives, you had to use the limit definition. Then you used that definition to come up with shortcuts. So we're first going to start with the limit definition. We're going to start with x. And the notation is interchangeable, right? So it just depends on the mood that I'm in. Limit as delta x approaches 0. And notice by necessity, direct substitution will always give you 0, 0. And you have to simplify. Thankfully, no one can do partial fraction decomposition of these. Expand out that x plus delta x squared first. I'm also going to show you the two through right after. Actually, looking right that way. Right that way. There is your first term completely expanded out. Now comment on notation. Are they the same? Nope. What's the left-hand side saying?
Both terms are squared, and the other one is saying just that it's squared.
Both terms?
Like it's saying it's you're taking the like it's squaring the derivative, right?
So first off, it's not a derivative, right? Delta isn't derivative.
Oh,
Delta's change. But yes,
you're squaring.
your idea is correct. You find the change first and then square it. That's the left-hand side. The right-hand side is change in the squares.
Yeah,
Right. What about this?
that would be finding the change twice.
that's actually that is an actual operator, delta squared, but it's in a more advanced math course typically. I think that appears in physics. Right, so that's not even like change squared or anything like that. That is just a different operation. It's a different operation altogether. And so you have to be careful with the notation. It's the same thing why I wrote this. Are they the same? They could be. It's ambiguous. Yeah, is that so? That's where you have to look at this and you go, is that delta of x times y, or is that delta x then times y?
Could you not?
It's ambiguous. You could put parentheses around the delta x to also avoid the ambiguity. So you have to be careful with your notation.
Could you not also just do delta parentheses x close parentheses y? Why would that not be the same as delta x?
Because delta x itself is a quantity. You have to take the delta and the x together.
Gotcha.
Would that
Because it's saying chain of x, not.
would that be incorrect? I don't actually think so.
Because this is delta.
It's not. It's not what we would normally write. But I don't see anything wrong with it. Unless you get into more advanced and delta itself is a separate operator. So I would avoid doing that. Because delta itself might be an actual operator. In which case you're going to say it's that operator operating on x and not change of x.
Is that not what it's saying? Isn't the operator like change in this case?
Not necessarily. Delta itself isn't anything. Delta x means change in x. Right? But delta itself that might actually be an operator. I don't know it off the top of my head. Which would be a different thing, right? If you did delta parentheses x, that would be whatever the delta operator is on x, versus delta x together, which universally means change in x. There's only so many letters in the alphabets. They tend to repeat.
My physics teacher was like, I can't wait until they start using emojis in physics when they run out of Greek letters to use.
So by the way, the del symbol has another meaning that we actually examine in this course as well. It means boundary. So if you do like delta capital S, that means the boundary of S.
Like, why not just make up symbols at some point? Like, why?
There's only so many symbols you can make up, so
Why use the same ones over and over again?
I couldn't tell
That
you.
just seems confusing.
It's above my pay grade.
It's not much physics.
2x squared minus 2x squared, we have a minus 3xy, a plus 3xy, plus 4y squared minus 4y squared.
So are you always going to do like those just the terms with dx? Or delta?
You should, because the terms are being held constant, right?
So could you just look at it and just note that and just say?
You have to be careful.
terms cancel?
You have to be careful. Yes, in general you can, but still write it all out. I'm also factoring out a delta x.
Where did the, see what's,
Good question. And now what's the limit of what remains?
negative 3, 1.
2,
x.
Oh, it's,
Oh, yeah.
okay.
It's only delta
I
F equals
was
zero.
gonna say, wait, why is there next to it?
There's your partial with respect to x.
So it's basically just a lot of other, and then working through zero.
Well, it's just like taking the derivative in count one. And this is the only question that I use the limit definition on. Point is to show you, go back to the function, take its derivative with respect to x, treating y as just a constant value. So think of y as like 1. Take the derivative. Derivative of 2x squared power away, 4x. 3xy, that's kind of like 3y times x. 3y is your constant multiple. That's just 3y, right? It's just the constant multiple. 4y squared is constant. Derivative constant 0. You're left with 4x minus 3y. Just what the limit definition tells us. And remember, what's this saying? It's saying that delta x, or x is the only thing changing. Right? Everything else is being held as a constant. With respect to y, and then do the same thing as before. We're going to expand. Two x squared minus 2x squared minus 3xy plus 3xy, 4y squared minus 4y squared. Every term we're left with has a delta y. And what's the limit of what's left? And if you go back to the original, you just take its derivative while treating x as a constant. 2x squared goes to 0. Negative 3x times y, that negative 3x is your constant multiple, so that partial is just negative 3x. And obviously 4y squared, 8y. So that is what the definition is saying. And that's all there is to taking partials, by the way. It's very simple, very straightforward.
So why not just, I guess, this is just a representation of how it works, or why not just take the
We're going to. But this is why that works, because of this definition. And so again, remember back in Calc 1, you studied the definition of a derivative and you used it at first to see what's actually happening.
So I guess on an example, you wouldn't have to do this.
Unless I tell you definition. Because now I'm not going to. I'm just going to straight up take derivatives. With respect to x, you treat y as a constant.
And so then this is where the del symbol comes in.
So again, it just depends on my movement, what I'm going to use.
Yeah, you're right. I don't know why. Type 3 isn't very difficult. I feel like this would have made a lot of the work like way easier.
Well, yeah, because to prove exact, you need conservative vector fields. You need the idea of conservative vector fields, which is partials.
So there are sometimes I'm sitting in the EQ and I'm like, what is happening?
This is
What are we doing?
I don't understand it. But again, it's above my pay grade. Well, the 1 over y acts as a constant multiple, right? What's the derivative of x squared with respect to x?
2
Now multiply that by 1 over y. Y squared is your constant here, right?
Mhm.
Derivative of 1 over x.
No.
X with negative 2. Negative x.
Yes. Negative x is negative 2. We're negative 1 over x squared. Multiply by y squared. There's your partial with respect to x. Partial with respect to y.
Is negative y squared over x squared, or negative x squared over negative over y squared. Plus 2y over x.
There are your two partials. What's the derivative of a sine? Now you have to do chain rule, right? Now what's the partial of the inside with respect to x?
2 plus.
2 plus 3.
Just 2.
Just 2. Otherwise a constant.
3y drops away.
There's your partial with respect to x. Right. Derivative of sine of u is cosine of u times du dx. The function stays unchanged. What about with respect to y?
3 cosine of 2x plus 3y.
There's your two partials.
Is it? Inverse tangents again. Or yeah, I guess I'm confused.
So the general rule for inverse tangent. What's the derivative of an inverse tangent function?
It's really not a question, isn't it?
God, I wish it was. And people are trying to retire.
1 over u. 1, no, 1 over 1 plus u. No, okay, not sure.
It's like close with secant, isn't it? Something.
You said you had me for Calc 1, so this makes me very upset.
Is it contingent?
One over 1 plus u squared.
Okay. What am I thinking of with secant then? Is there's a secant tangent relationship there?
Derivative of tangent is secant squared, derivative of secant tangent
Derivative of tangent, that's.
is secant squared. But this is a tangent.
Yeah.
It's inverse. Alright, so partial with respect to x. Well, you know you're going to need u prime in the numerator. So you're going to need the derivative of x squared y with respect to x in the numerator.
So it's
What's that partial?
2x. Just
2xy. Y is a constant multiple.
Oh, never mind, they're not being multiplied together. Okay, never mind.
Over 1 plus the square root. We're taking the inverse tangent of. Plus, what's the partial with respect to x of xy squared? Just y squared, right? Over 1 plus the square. There's your partial with respect to x. Now, with respect to y, what is it?
It's just
Square.
Oh, wait. No, it is just.
1 plus
Yes.
x over y.
Two x one over 1 plus x to
X to the square.
Oh. Oh, yeah.
There you go. There are partials. So it's literally the exact same thing as Calc 1, just with that now added caveat. So again, general exponential. What's d dx of e du?
Or no, one over
E to the U.
It's not just e to the u, not u.
U.
It's not u.
Oh.
U prime.
Yeah, yeah, sorry.
Is it that interval that's more than
No. Antiderivative dx is e to the x. When you deal with that, you have to do stuff. But you have to be careful because that would only work if it's a constant.
Yeah.
Like, for instance, e to the x squared has no antiderivative. Partial with respect to x. Again, you're going to need that u prime. What's the derivative of the exponent with respect to x?
2x.
2x plus, yeah, plus 1. And then e to the x.
There's your resistance of x. And what about for y?
X squared plus x.
No, it's just x.
Oh, yeah.
And x squared is a constant with respect to y, so it's
It's hard to travel. Still getting used to that.
and you'll get pounded. It's we move on to the next topic, and you'll just go out of that. You struggle with that.
Also, it's like, no resistance.
But now, differential equations start to make a little more sense.
Yeah,
At least now you know how to take partials.
This would have been useful knowledge going into that.
Again, why is it only Calc 2 that's appearing? I have no idea.
Do we already learn partials in Cal, or sorry, E, like last week or not?
We had to use it already. Remember exact equations?
Yeah.
Yeah.
That the card partials.
this wasn't used for that.
So again, you could get away with just partials on that, but technically you should have conservative vector fields for that, because that's what we're doing. But if you know how to take partials, it's fine.
I'd appreciate it if you reworked the curriculum so that we learned this stuff before we got to the
No, but you have to understand the geometry of space first. So you actually have to do that stuff before this. I would like to see vectors be done in Calc 2. I would like to see a whole rework. Calc 1, Calc 2, Calc 3.
This is what you're proposing.
Because Calc 3 is called multivariate calculus. It should start with multivariate functions and only cover multivariate functions. I mean, maybe start off with the geometry of space, which would include a little bit of vectors, but then you have to waste so much time on defining what a vector is and all that.
I think it's like.
But again, what do I know? What do I know?
Like, because even for you, like, isn't this like, it would help with statics and dynamics and stuff like what you get, and then also it's pretty
Knowing how to
like, all, like,
do knowing how to do matrices would have been like super useful for static. I literally had to have like pretty much like my best friend in college. She's like insanely good at math and physics. I was like, Robert, how do you do this? And he's like, all right, you're just gonna have to trust me because I don't want to get into the full explanation of it. But here's how you do it. Because just believe me. I was like, okay, cool.
It's just how it is.
He was like, this is just how it is. I don't have time to go through the like logic of why.
So those are the partials, right? But aren't those also functions of x and y? So couldn't you take partials there?
Yeah.
It's called your second order partials. How many are there? How many second order partials are there? So I'm not asking how many higher, just we can take the second order. How many second order partials do you have?
No, so you can do partial x, partial y, partial x, partial y, x, partial y, y, 4.
You have 4 second order partials.
Could you
However, only 3 of them are distinct.
explain that? Why do 4?
Can't you take the partial with respect to x?
Yeah.
So that'd be this.
Okay.
But couldn't you also do it with respect to y?
After you take the first x. So x, y.
Oops, sorry, I did that wrong. It's called a mixed partial. Because that's a function of both x and y, right? So you can take its partial with respect to either x or y. So that gives you 2, just from that first partial. And then same thing for the y. You take it again with respect to y, or respect to.
So like when we do the Dell
I'm
one,
just gonna assume
the 1 year paintings, like for example, the second one, this always first.
I'm like,
Because what are you doing?
Partial f.
It'd be partial partial x.
I was
That's why it's in that
like
condition.
celebrating this.
But it actually doesn't matter.
You're like, yeah, that's magic.
Because Claret's theorem, the order in which you take a mixed partial does not matter.
Okay, that would be equal.
So these two are actually identical. The order in which you take it doesn't matter. They're the same. So you have 4 second order partials, but only 3 of them are distinct.
Okay, so you're taking the 2 partials at the top with respect to X and Y. You're taking.
So treat, so these are now new functions, just treat them as new functions, like G.
So you're taking.
Then you can take G with respect to either X or Y.
Okay, I see.
Right, say this is H
So you.
with either respect to X or Y.
Okay, so once you get the first partials, you can then take them again.
You're taking the
With respect to you.
Yeah.
Because it's still a function of those two independent variables. So how many third order partials would there be?
Too many.
What do we say? No, 3 factorial?
8. 2 cubed. Right? Because
Oh.
this would have 2, this would have 2, this would have 2, this would have 2.
Oh, so.
However, it's not 8 distinct,
So is it,
because the order in which you do the mixed partials doesn't matter.
so for finding out how many partials there are, like non-distinct, you just take how many variables you're working with?
Raised to the order.
Raised to the, okay.
So if you're dealing with 4 variables and you're asked for second order partials, you have 16 of them. You have 16 non-distinct.
That's insane.
Why would anybody want to be in that?
No offense.
Because math is the language of the universe.
Yeah,
I mean, you want to
We
use
had
it
this
as
discussion
balance.
already.
yeah, I know.
If you're religious, it's God's language.
It sounds a lot cooler when you put it like that.
And this is the language of the blueprint of the universe.
Yeah, it sounds a lot cooler when you put it like that.
Math is its own language, by the way. So I can say that I'm multilingual. Because I speak English, I speak math, I speak Wolfram's own language, I speak a little bit of Python.
You probably know the language that is most.
I'm actually now starting to get comfortable with LaTeX,
Oh, yeah.
so 4 languages I speak.
You probably, I mean, math is probably the most applicable language because it's standardized.
It's also standardized in terms of the universe. So
That's a crazy thing.
we want to find all second order partials. All right, so first off, how many variables are there?
3.
So how many second order partials are we going to have? 9. How many of them are going to be distinct?
Okay.
6, I think 6 is right.
How do you?
Because all the mixed order partials are the same.
Oh, okay. So then it's, I guess to find the distinct ones, you just take.
It will be 6.
You just take the amount of variables you have.
Because X, Y, so X, Y, and Y X will be the same.
Yeah, so what I'm saying is, could you just take the amount of variables you have and multiply it by the, so that you could just.
I think it's
do
minus,
times-
yeah, minus 3.
3 times 6, and then you just say,
I think that's in general house.
so I guess to find all of the.
So actually, I think it's going to be, not that it be minus the combination.
Two?
It's a combination kind of thing.
Oh, so you take, so it's 3 to the power 2 minus 3 in this case.
Distinct.
3 squared minus how many,
Yeah.
minus how many ways can you order 2 variables?
2 to 1.
Out of 3.
Three. No.
D3 choose 2.
Yeah.
Which is 3. Right, you have 3 variables, you have to choose 2 of them.
You're getting.
It's combinations. Yeah, it's a counting issue. Right, so if it was third order, it would be
Six.
it wouldn't be 3 choose 3 because that's 1. Or debate.
So this is a slightly.
Oh, I'm sorry, it's not combinations, it's permutations,
Two,
I believe.
3P.
So this is a slightly related question. When would we be using this stuff? I know that's kind of like everybody's math question.
Don't worry, we'll get there. We'll get there.
Like a combination or a permutation?
Partial derivative.
We'll get there. Right now, we're just learning about them. You're going to use them a lot.
I mean, if you use it in statics,
What's that?
you use it in statics.
Secondary
Statics was more like,
It was like statics is like everything is like equilibrium based, so you can kind of like solve.
you either set it to, well, statics you set it to 0. Dynamics you set it to.
Static means
Either
Static.
constant
Static.
motion or
Yeah.
still.
Yeah.
And so statics is so much fun.
dynamics is more fun.
Statics.
Actually, dynamics is also more.
Some of the forces.
You really want to take a fun course? Chaos theory.
Oh.
Universe is chaotic. So it's essentially a step above dynamic. It's chaotic.
Chaotic. I didn't like my dynamics class because like we didn't have the right license.
Let's partial with respect to x.
You need to take labs for that. That's
We need to do cosine to one.
I was just all lecture for statics. Maybe the one thing for statics.
With respect to y,
Minus x sine y.
with respect to z,
Minus xy sine y.
What? Wait, why is the first one not?
That's because it's respect.
Oh, because that's just constant. Because it was nice.
now start with that first partial. We'll do this systematically. Take it first with respect to x.
Zero.
0.
Now, with respect to y.
Negative sine. Or, no, negative z. Sine. Y z.
With respect to z.
Y. Sine. Y z.
There's our first batch of second orders. I'll move this over. There we go. Okay. Stick with the same order. First, take its partial with respect to x. What do you get?
Negative c sine y.
With respect to y.
Negative x. Z squared. Cosine. Oh, y z.
Now with respect to z.
Negative x. Y. see. Negative x, y, plus 7, y, z.
Because with respect to these like two. Oh, no, it's wrong.
That's a function of z. Isn't this also a function of z?
Yeah.
This is product rule.
Oh.
So I agree, that is a term. What's the second term?
Plus, or it's minus.
Yeah, in this case it'd be minus because it's already a minus.
Minus x sine y z.
There's your partial perspective z. Yes, you have to keep in mind products and quotients. All right, so look at now the partial with respect to z, do it with respect to x. What do you get?
Negative y sine of y z.
With respect to y,
Negative x z sine of y z.
no.
Or, no, negative
X, Y.
x sine
Yeah.
y z. It's
Yes, it's a product rule again, isn't it?
plus negative minus x sine of y z.
And then with respect to z.
Sine, or no, negative x y squared sine of y z, or no, cosine of y z plus.
Nope.
Oh, yeah, no.
It's just with respect to z.
Yeah.
Those are the 9 second order partials.
That's,
Now, verify Clairaut's theorem. xy, yx should be the same, are they?
Yeah.
xz, zx should be the same.
Yep.
yz, zy should be the same. So 9 second order partials, 6 of them distinct. Right? Because x, y, yx are the same, x, z, zx, and then y, z, zy. So 3 are going to repeat. Use Clairaut's theorem to your advantage. Let's say you're given, like a 7-variate function, and you're asked to find a 4th order partial, a 4th order mixed partial. Use Clairaut's theorem to your advantage. Because a lot of times, a specific order might eliminate terms. Because maybe one of the terms in your function doesn't depend on one of these variables. So if you take the partial with respect to that one variable, it's not a function of, it goes to 0. It's constant. So that immediately eliminates one of the terms of the derivative. So pick a convenient order to take its derivative. Use Clairaut's theorem to your advantage. You should have studied in Calc 1, at least been introduced to the notion of a differential equation. And obviously, two of you are taking differential equations. Those are ordinary differential equations, because it's dBx. Well, we also have what's known as partial differential equations. It's the same idea, except it involves partial derivatives instead of regular derivatives.
So I'm gonna do all like homogeneous and all
Different. It's completely different terminology when expecting on partials. Again, we're just going to be looking at some simple partial derivatives, basically when I even solve them in this course. Because actually, even the most simplest are more complicated to solve than some of the more complicated ordinaries. There is a course, partial differential equations. It's a junior level math course that goes over some of the techniques. One of the more well-known partial differential equations is known as Laplace's equation. There are two others really well-known. You have the wave equation and the heat equation. And you will study those in depth when you take partial differential equations. Because there are tons of solutions to those.
But is that the same as the equivalent and gain one or no?
No, that's Newton's law of holding on state. Heat equation is from thermodynamics. Wave equation is from mechanics. Specifically wave mechanics, but mechanics. So this is Laplace's equation. Zxx plus zyy equals 0. All we're being asked to do is determine which of these three functions, and there could be multiples or there could be none. So which are solutions to Laplace's equation? To be a solution, it has to be when you plug the function into the equation, it's satisfied. So we'll start by looking at Z sub 1. Let's see if this is a solution. What's the partial with respect to x? You're right, it is a constant. But in this case, it's a constant multiple. Right? And what is with respect to x again? What's the partial with respect to y? With respect to y again? Z1's a solution. Zxx plus zyy has to equal 0. Z2. So I technically should have done here Z1x. I should have done these. We get the idea. And in such case, you may see something like this. What's the partial with respect to x? In fact, that will be non-zero for every value of x and y. Right? Even an exponent can never give you 0. But it doesn't matter. Even if it gave you 0 at an infinite number of points, if even at one point it's not 0, it can't be a solution. Right? So it has to be a solution for all possible x, y. And then Z3. Partial with respect to x.
2x. Two.
And so Z1 and Z3 were solutions and 2 was not.
So I guess this just still like cancel out different ones. Or
It's all the second partial, right? Never the first
For the
one.
Clause's equation, yes.
like, would you use the process equation to just cancel out some of them?
Oh,
So
I-
just be like, this is
It's just an equation. I honestly don't know what it represents.
so it's not really used for anything. Like
Oh,
that?
it is. I just don't know what it is off the top of my head.
Okay. Fair enough.
Like, it represents something. I'm sure it represents something physical, some kind of physical phenomenon. I just don't know what it is off the top of my head.
Physics phenomenon, like, things in
Versus something like over here.
And does the transform have to do the same, like, similar to the equation, or
What do you mean transform?
Laplace transform?
Oh, that's something different. We'll study that in the differential equation. It's just it's a transformation. So that is the wave equation. Right, of course you can extend it to however many dimensions you're in. Right, this is generally speaking in physics, you deal with three spatial, one temporal, so you go with 4 dimensions. So that's the wave equation in 4 dimensions.
How come on the top, it's funny, it's like it's after the del, but at the bottom it's after G.
Well, remember, think back to calculus 1 notation, it's the same thing, right?
Oh.
So the top, that del squared says it's a second order partial. The partial t squared there means it's with respect to time twice. Right, so it'd be partial t in the denominator. And we just simplify that to be partial t squared.
Because you're taking the
With respect to t twice.
I guess you could say it's like,
Just like d squared over dx squared means second derivative with respect to x.
yeah, I guess you could think about it as like del over del t times del.
Not times.
Del t
Not times, of.
of. Okay, and then all.
Right, because del partial t is an operator. So you don't multiply operators. It operates on something.
Gotcha. So of and then of u.
Well, it wouldn't be of.
Or I guess
It'd be partial t of partial u partial t.
Okay.
Right, you're operating on
U.
the first operation of on u.
Yeah. So I guess it's just saying you're operating on u twice.
But with respect to G.
Well, you're not operating on U twice. I mean, no, you're not. You're operating on U once, and then you're operating on what you just operated.
Why would that not be the same thing as twice?
Because you're not operating on U twice.
Okay.
There is
I
already,
get what you're
right?
saying. Because
You operate on U once, and now you have a new function
It's
operating
the
on.
difference between 2x and x squared.
Right.
Yeah.
I'm not operating on U twice.
Yeah.
I first operate on, and then I operate on that, on what we just
operating
operated.
on it again.
Yeah.
Not twice, they're operating on it again.
So that is the wave equation, which is a very common partial differential equation that's studied. And then we have what's known as the heat equation. Which is that. Right, so generally speaking, you're dealing with 3 dimensions, 3 spatial, 1 temporal. It would be ut equals uxx plus uyy plus uzz. Let's see if that's actually on here. Right there, alpha, some coefficient times that sum. This is the heat equation in 3 dimension, in 3 spatial. And again, that is a very common function that's studied in partial differential equations. In fact, going back to when I took it, 90% of the class was those 2 equations, studying those solutions. The other 10% was how to get those solutions. So it's essentially just methods of solving these 2 equations. And then, of course, you have nonlinear differential. Notice those are linear, by the way. You have nonlinear differential equations, and the most famous nonlinear differential equation is the M-body problem, or the N-body problem. So if you look at the Earth and Sun, that's a 2-body problem.
But if you include the moon, then it's 3.
But if you
Now, if you include the Moon in that, that's a 3-body problem. By the way, that doesn't have an analytic solution.
everybody problems.
So how do you numerical in school?
It's only up to 2-body that has analytic solutions. Everything above 2-body has a non-analytic solution. You have to do numerical. Well, solar system is not a 3-body problem. It's not even a 9-body problem.
Oh, okay.
It's all the moons, I don't know.
The astro.
You also have to do the asteroids and comets. And
Do satellites count?
technically, yes. But generally speaking, we ignore what men put into orbit.
Things that are negligible? That's crazy.
Typically speaking, we ignore them. Because when we saw the N-body problem, we were typically just looking at
Big mass.
the universe itself, not human intervention. But technically speaking, what we put in orbit does affect the solution. So we have to take all that into account as well. And by the way, all the satellites that we also launched that are leaving the solar system would be part of it.
So like Saturn, it's made out of like a bunch of rocks and stuff. Is that included in there? Or would that be included with Saturn?
They would technically be included.
What's the gas giants?
The rings.
Oh, the rings.
But all the gas giants have rings.
Saturn's just
Saturn is the only one that's visible though. But they all technically have rings. Of course, those solutions are fun. I got pissed because someone posted an article, solution to the 3-body problem found. So excited, I'm like, reading it. No, it's a fucking numerical solution. This isn't a solution. Get my hopes up. It was a clickbait title. Bastards.
They got a solution. It's not.
That's not what the headline was implying. The headline was implying an analytic solution. Because anyone who studies it, they say we found a solution. It means analytic, not a freaking numerical solution.
I see. This is a Wallace interpretation.
What you would say if it's a new numerical solution is a new solution has been found. Not a solution has been found.
In the spirit versus what letter of the
They did it just to get clickbait. Bastards. That should be illegal. Guaranteeing the physics student they're already punished. Those are two types of partial differential equations. Any questions on partial derivatives?
How about chain rule?
We're going to study that separately.
Oh,
Yeah, we are studying that separately. When did we study that actually?
that's fine.
Yes. We actually will study that next class. Tangent planes, differentiability, and chain rules.
Something cool to see.
I'm not looking forward to having this stuff.
So on the next exam, is it everything from the start, or is
No.
it just after exam?
The only comprehensive exam is going to be exam 3. And that's because I'm required to make it comprehensive. Which is
But
annoying.
is it gonna be comprehensive in the fact that like there's a little bit of stuff here and
Yeah, it's
and
just
then
gonna
all of like
Majority is going to be new stuff.
it's just gonna be
If I even do that. Summer, I might be able to get away with not making it comprehensive. We'll see.
you can just claim that it's comprehensive. Who's gonna track?
You'd be surprised. They can require me to submit it.
Do we have any of the exams?
Boo.
I'll submit the exams once they ask for it.
You can make one to submit and only you give.
You should
Now
only
we're
read
on
the
to
exam.
some- now we're on to something.
So new homework available, all right, homework 7. I mentioned it now, but the third quiz is available after next class. And it will be due Monday. And second group assignment, you don't have that much time to work on it. It covers only this multivariate stuff. Also on there is something I'm not covering in class, optimization, multivariate optimization. So you're going to be required to read that section on your own.
It covers something else.
It's covering something that I'm not covering in class, but it's in
It's
textbook.
in the textbook.
So the point of this project, not only to test that, is also to teach something new. Applied optimization. Because you may need it.
For what?
So while I'm not covering
I
class,
wanna know. For what?
well, you've optimized single variant, right? Nothing is single variant.
Will I ever be getting
Yes.
paid to do this?
Yes,
As an engineer?
yes.
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 Really?
Are engineers supposed to optimize?
Don't believe
Yes, that's true. That's true.
But not comp sci. No, comp sci do, but it's like different.
So, yeah, go using.
It's like efficiency.
Yeah, like ON and.
So next class, we start with this worksheet. Then it's tangent planes, differentiability, and chain rule, and that worksheet. So you have 2 worksheets next class. See you then.
Also, I get early Wednesday off, so I will have to reach like the evening on Thursday.
Professor's
You're gonna have to email me.
Okay.
Professor's open.